and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will discuss calculating magnetostatic fields. Just as we know that charge distributions that do not vary with respect to time can generate electric fields, similarly current distributions that do not vary with time can generate magnetic fields. If you go back to Maxwell's equations, then there are two equations which tell you how the magnetic field in space is related to the electric fields. For example, you have the Maxwell law, that is curl of the magnetic field H is given by the conduction current or the current distribution J plus the displacement current del D by del T. Similarly, you have del cross E, which tells you how the electric field is changing with respect to space and time, being related to the magnetic flux density vector B. Okay. But we are going to consider a scenario where the current is assumed to be stationary, that is to say we assume the current to be steady or DC. In such scenario, there is no time variation, the current is constant with respect to time, and there is no displacement current as a result of it. Similarly, the magnetic field is not changing with respect to time, and therefore del cross E will be equal to 0. In fact, del cross E equal to 0 together with del dot D equal to rho V constitutes all the laws that we call as electrostatic. That is, these laws are sufficient for us to tell what is happening or how to calculate the electrostatic fields. Because this displacement current is removed, what we have for the curl of the magnetic field is only the conduction current J. And this conduction current distribution, if it is known, will allow you to calculate the magnetic field H. Okay. So, this is the differential form of the Maxwell's equation or the Maxwell law. There is an integral version of which you should all be familiar with by now, which tells you that integral of the magnetic field H over a closed curve must be equal to the total current that is enclosed. Together with this curl equation, if we supplement the equation with del dot B equal to 0 and we consider a medium where B is always equal to some mu naught into H, this is the so called non-magnetic medium. Okay. So, if we specialize only to the non-magnetic medium, then B is equal to mu naught into H and the divergence of B is always equal to 0. So, together these two laws or these two equations can be used to compute magnetostatic fields. Please note that if we consider a current in an extremely thin wire or a filamentary current as we would call it, then the current is assumed to be not varying with time. That is, if you plot the value of the current carried by this particular wire, then it would have some value, whatever the value, let us say it is I0, the wire is carrying a current of I0, this value will not change. Okay. If you consider, so that is why this is called as a direct current or a steady current. On the other hand, if the current were to change like this, then this particular current, which would be changing with respect to time, would be called as the AC current. Okay. Sinusoidal currents are a very special type of AC. So, in this module and the next few modules, we are only going to look at the DC current is a slight misnomer. It is direct current, but that is okay. The abbreviation of DC and AC are so widely used that we call DC current and AC current, although strictly speaking we should simply be calling it as DC and AC. Anyway, we consider that the current distribution is known, and from this current distribution we want to find the magnetic field H and sometimes also find the magnetic flux density B. In addition to this Ampere law, there is another law which is called as Biot-Savart Law, okay, which was discovered almost simultaneously as Ampere's law, and this Biot-Savart law is also sometimes useful. It tells you that the magnetic field, because suppose if this is a wire that is carrying a current and we assume that this particular current has a certain value of current I, and this dl prime is this short segment of the wire which I have marked in the blue line. So, I do not know whether you will be able to see this, but if you are able to see this, then this blue wire tells you what is the short current element dl prime, and carrying a current of I, the element will carry a total current of I dl, carries a current of I. So, this magnetic flux density dB at any point. So this is the point at which you are trying to calculate the magnetic flux density dB. Then this dB will be given by mu 0. I am assuming that the space we are considering is free space or non-magnetic, therefore mu is a constant mu naught, I dl prime cross r hat divided by 4 pi r square, where r is the distance from the current element to the point P. So this vector r is the vector from the current element to the point at which you are evaluating the field. And the condition that you are actually seeing here is that this particular field dB that you calculate at the point P will have to be perpendicular to the current element as well as the vector r. So in fact, if you consider this current element and the vector r, okay, then the magnetic field will have to be perpendicular, either it is coming out of this board or it is going into the board. Whether it is coming out or going into the board is decided by the right hand rule, and the right hand rule tells you that if you curl your fingers starting from the current direction to the vector r, then the magnetic field must follow your right hand rule. So to show you that, if this is the current carrying element, then if I enclose, right, the current by my fingers, then the thumb will be pointing along the direction of the current and the magnetic field will be encircling. So at a particular point, for example, if this is the current element and this is the point, then the magnetic field must be perpendicular. So the magnetic field you have to imagine as coming out, and for the plane that will be formed by this current, my thumb and this pointing index finger, if you take that plane, then the magnetic field will have to be perpendicular to it. So I can't show you this perpendicular thing, but this is how the magnetic field should be looking like. So this is the right hand rule which allows you to determine the direction of dB. The magnitude of dB can be obtained by simply taking the magnitude of this expression. Okay. The expression for Biot-Savart law that we have written is applicable only to what is called as filamentary current. That is, you have a wire which is almost having no cross section, therefore this is a thin wire that we considered. But in general, if you for example consider a microstrip line on a printed circuit board, then the width of the microstrip line cannot be neglected. So the current will be flowing here, no problem, but then the width of the microstrip line cannot be neglected. In this case, it is more common to talk about the volumetric current density vector J, okay, and the total current that would be contained in a particular, this one will be given by integration of this volumetric current distribution J over the entire volume where this particular J is defined. So the corresponding expression for this dB, or rather, since we know that a small wire segment cannot exist, the correct form for the Biot-Savart law, although this is okay for the filamentary or an extremely small current element IDL prime, but the magnetic field that you need to calculate must actually be obtained by integrating this particular expression. So you will have to go over the entire curve through which the current is flowing, and once you do that, you obtain the full magnetic field at any point R. So if you remember, this is what we called as the field point. These primes are used to denote what is called as the source region or the source point. So as I was saying, in the case of a microstrip line on a printed circuit board, you do not have a thin wire approximation because there is a considerable distribution, and then the proper way of specify its volumetric current distribution J. In that case, B of R needs to be obtained as a volume integral. So this will be mu naught J. So that would be J at the source point, which would be J of R prime, and what is the volume element. So if you imagine that there is actually a small volume that we are going to consider here, okay. So this small volume shown in the blue line through which the J vectors are all coming out, that corresponds to the current element now. So you do not have a current element in the form of a line, but you have it in the form of a volume times R hat divided by 4 pi R square, where R is again the distance from the volume element where the source is located to the point where you are actually calculating the magnetic field. So this is the more general form of Biot-Savart's law. We will be using this form, or we will be using the filamentary current form depending on the problem that we are going to calculate. Okay. So, with all of this said, let us now proceed to calculate magnetostatic fields for a few simple and important cases. In some sense, calculating magnetic field is slightly difficult, okay, than the corresponding electric field calculations. Why is it difficult? The difficulty comes because you have a cross product over here, okay. Because of this cross product, your signs and the directions will be slightly non-intuitive, okay. Therefore, you have to pay particular attention to how you define this dl prime, that is the source distribution or the source line elements, and calculating this particular unit vectors r from the source to the field point, okay. So, we begin by a simple example of an infinite line charge, okay. So, this is my x, y and z coordinate system. Let us assume that there is a wire which is actually going all the way to infinity, okay. For clarity, I show that this wire has some cross section, but in what I am going to assume is that this cross section is actually 0. So, the wire extends from minus infinity to plus infinity. We assume that the medium is some mu, okay. Mu could be mu naught, or you can have a medium with a constant permeability. So, it would be mu r into mu naught. Either way, we can represent this one by just giving you mu, okay. And then I will tell you, in the medium which is air, use mu naught, or if I give you a magnetic medium with some scalar magnetic permeability mu r, then you can replace mu with mu r and mu naught, okay. Now, having said this, let us now try to calculate the field. So, to calculate the field, let us say I take the field at this particular point, okay, which is shown by this red color dot, okay. There is a certain vector which is the position vector. So, at this point we will mark as P. So, the position vector that starts from the origin and goes all the way to the point P is the field position vector R, okay. However, I am supposed to consider the current element at this particular point, okay, on the wire, and let us consider the infinitesimal, the element length to be dz prime, and it is located at a height of z prime from z equal to 0 plane, okay. So, my source point can actually be written as r prime is given by z prime z hat, okay. That is, I am assuming that dz prime is actually very, very small, whereas the position vector r, which joins, or which is the line that is joining the origin O to the point P, is given by a r hat plus z z hat. What is this a and z? Well, you know, if I consider the projection of this line OP onto the z axis, okay, and consider that this particular projection is constant, and imagine that there is actually a cylinder sitting up here, okay. So, this is a cylinder, then the radius of this cylinder is taken to be a. So, a is just a point which I am considering at P, which is projected onto the z axis, or the height above the z equal to 0 plane where I consider this point, okay. I am supposed to consider the radius of this one. So, this height OP projected onto the z axis is the z value that I am considering. The radius which I consider is the radius of the cylinder, which would be about a, okay. So, the radius of the cylinder that we consider will be a, and the height over which this one would be present on the z axis will be z. So, therefore, the position vector r, okay, we have to define, so we have to mark the position vector r over here. So, let me try and mark it from this. This would be the position vector, the green vector will be the position vector, because that is what goes from the origin dz to the point P. So, we are assuming that we have a general point P where the radius of this cylinder, you know, you have to imagine that there is a cylinder over there with a radius of a, and the projection of P onto the z axis will tell you what is the corresponding z coordinate, okay. So, we are assuming that this is the point where we are going to calculate the field. So, we were considering this radial distance r from the source point of the wire to the point where I am calculating the field. So, this r now is of course defined as r minus r prime vector, correct. So, this is the position vector of the field and this is the position vector of the source, and I know these two values in this cylindrical coordinate system. So, I can write this as a r plus z minus z prime into z hat. Now, we have all the tools that is necessary to apply Biot-Savart's law, and to calculate the magnetic field dB at this point, which of course will be in the direction of phi, as you will very soon see. So, this is mu naught I by 4 pi, which is the constant. So, mu naught I by 4 pi, okay, times what is the current element that we were considering, I into dz prime, right. So, this is I dz prime, and the current element itself is located along the z direction. So, this would be dz prime z hat cross a r hat plus z minus z hat times z. So, this vector is your capital R vector, okay. Of course, that is not, so that is the vector that is there, divided by, so this entire thing divided by r square is the magnitude of this particular r, and that is given by a square plus z minus z prime whole square to the power 3 by 2. Why have I put to the power of 3 by 2? Because if I take this r square and then I want only the unit vector along r, okay. So, if you go back to this one, this is the unit vector that I am trying to find out, and the unit vector r hat will be equal to the original vector r divided by its magnitude, and we have 1 by r square in the Biot-Savart's law, right, multiplied by r hat. So, this 1 by r square into r hat, this r hat can be written as the complete vector r, divided by the magnitude of the vector r, and this when you multiply this you get r to the power 3. Since r itself is given by a square plus z minus z prime whole square under root, taking this r to the power 3 means you take this particular quantity onto the right hand side to the to the power 3, and essentially obtain this equation. So, I hope that you are you understand what is going on here. The radius of this cylinder is considered to be a. This cylinder does not exist, you have simply imagined that there is a certain cylinder out there, and you defined r prime, which is the source point, and the source is actually along the z axis and located at a height of z prime. That is why you have r prime in this way. The field point r in the cylindrical coordinate system will have two components, one is the radial component and the other one will be the z component, correct. The position vector of r is given by a r hat plus z z hat, from which you define what is the vector r which joins the current element to the point where you are calculating the field, and from there you apply Biot-Savart's law. Now, you can evaluate this cross product here, z hat cross r, okay, because r, phi and z form a triad of the vectors in the right handed circular system. So, when I take z hat cross r hat, I will be obtaining phi hat, that is I will obtain phi hat, which will be the direction of the B field now, okay. So, this z hat cross r hat will be along the phi direction. There is a constant mu 0 I divided by 4 pi, and z hat, so there is I dz prime, z hat cross some z minus z prime times z hat will give you 0, because cross product of the same vector times same vector will be equal to 0. Therefore, the second term will actually drop out, divided by a square plus z minus z prime whole square to the power 3 by 2. So, this is the field that you obtain at the point P, okay, by Biot-Savart's law and the contribution of this current element, okay. The reason this field dB is written as dB is not in the usual sense of an infinitesimal thing. If this is the contribution dB, then you can actually repeat this experiment. This dB will actually be present in the entire region. It is not in, it is actually small, but at the same time it is present everywhere. So, it is weak field, that is why it is a differential field or the infinitesimal field that we have written, but at the same time this weak infinitesimal field is also present everywhere, okay. Now, of course, there is other, the entire line has to contribute to the magnetic field at the point P. Therefore, you need to sum up or integrate this expression in order to obtain the contribution of this element, next segment and so on, all the way from when z prime goes from minus infinity to plus infinity. So, you have to integrate this equation. So, I will do that right over here by removing this d here and then trying to put the integration sign from minus infinity to plus infinity with respect to z prime. Now, ordinarily this would be difficult thing to evaluate if the dependence was not on z but on any other coordinate point r and phi, because the vector phi is independent of z direction, but it actually depends on the values of r and phi. Okay. And because of this, so if you are not convinced about this one, you should go back to your coordinate system module, and then you will be able to understand what this particular statement. But in this case, only in this case, because the integration is carried out with respect to z, you can remove this phi from consideration. That is, you can remove this phi outside the integral. So which means that the magnetic field will always be along phi in this particular case. When you do that, phi will come out of the integral, and still you have this particular integration to perform. Since this is not a class on integration, I will leave this integration as an exercise for you to take it up whenever you are free. Okay. So instead, I will say the magnetic vector potential at the point P, which is at a cylindrical radius of A, is given by phi hat mu I by 2 pi into A. Okay. Now A is any distance. I can consider any other cylinder. For example, if I want to find out what is happening to the magnetic field at, let us say, this cylinder, okay, which is at a radius of r, then I can do that. So I just need to replace this A, which was just a placeholder for this particular case, by the more general radius vector r, and I obtain the magnetic field to be phi hat. It is directed along the phi axis, mu 0. So because this is the medium that I am considering, otherwise you have to replace mu 0 by mu r mu naught divided by 2 pi r. So if you look at from the top, you will see that if you fix the value of r, then the magnetic field is circulating in this way, and as r reduces, the magnetic field starts to become increasing in the amplitude. Otherwise this magnetic field will be circulating about the current that would be present over here. So that is the reason why you have this current rule, where the magnetic fields are circulating around a particular current carrying wire. Now you might say that, well, we have used Biot-Savart's law, but is there a simpler way to obtain this same expression? Well, there is a simpler way to obtain this expression. Now imagine that this goes all the way up to plus infinity, and below here up to minus infinity. I now want to find the field at this particular point, okay, which is at a radial distance of r from this particular current element. So from the current or the current wire, I am at this distance r. Now at this point, right, I am assuming that we are in the cylindrical coordinate system. You will have an option of h being along the z axis, or it would be along the phi axis, or it would be along the radial direction. That is, it could be either this way or this way, or it could be along the phi direction where it is circulating. Which of these components do you really have? Can you have a component along this direction? Well, you cannot have a component along this direction, because the current element has to be in this way. So if there is a current element in this way, only then there will be a magnetic field along the radial direction, and since the current element is actually along the z axis, there is absolutely no question of you having a magnetic field along the radial direction. It cannot have at any radial direction at all. Now can we have a component of h along the z direction? Well, for a component along the z direction, there must be a source of the current element which would be present in this loop, in the base z equal to 0 or some z equal to constant loop, and there should be a current element in this way. Because if there is a current element here, so this current element, if it is in this way, then there will be a z directed field, but there is no current element here. Similarly, there was no current element in this way. The only way that you have a current element is z, and surrounding that z would mean you can now circle this particular current. Therefore, there is only h phi component out of the 3 components. So that's the first thing that you will remember. I mean, that's the first thing that you will realize. So symmetry tells you that you cannot have a component along z, along the radial direction, or you can have a component along z direction. Well, not symmetry, but it's the source distribution that is telling you. But symmetry will now help us. What is meant by symmetry? Now we have said that the magnetic field can only be circulating this current element, and it would be along the phi direction. Okay. Can this magnetic field be dependent on the phi value? That is, can the magnetic field H depend at say 45 degrees from the x axis? Will it be different at 90 degrees? Will it be different at 180 degrees? Fortunately, no. Why? because if you go around, if you imagine that this is the wire, and then if you go around this particular wire at a constant radius, okay, phi is changing from 0 to 2 pi, the current distribution looks exactly the same. For the current distribution to look different, then if you are viewing this at 0 angle, if you are viewing this at 90 degrees or 180 degrees, the value of the current should have been different. But since this is an infinitely long wire carrying the same current I at all points, there is no dependence on phi. So, symmetry tells you that h phi does not depend on phi. Can I have h phi dependent on z axis? For example, if I am there on a constant radius r and I move up or I move down, but as I move up or as I move down, I see the same current distribution over there. The current is constant and hence there is no dependence on z as well. Can I now have h phi at least as a function of r? Yes, I should have, because if I am closer, then you can imagine that the viewing angle that you are seeing will be this much. Okay. So, you imagine that you are at this you have a very tall building and you are at some particular distance, and then you look at the building. So, you will see certain height of the building. As you move away from it, right, as you move away radially, the building height will also keep changing, or rather the more and more current elements start to appear. So, assuming that the building is actually going all the way from minus infinity to plus infinity, as you keep moving away, your viewing angle actually starts to increase. More and more current elements start to appear and they will contribute to a magnetic field. But the point is, as you keep moving away, you can distinguish whether how close you are here and how far you are there, and the field at these 2 points will have to be different. In fact, of course, the field goes down as a linear value of r, as we will show that one. So, what we have learnt from this exercise is that you can only have the phi component, and this phi component can only be a function of r. Therefore, if I have the current element and I am at a particular radial distance r, okay, which is a constant, then Ampere's law tells you that h phi, okay, along this particular radial constant, r d phi, which would be the loop that you are going to consider. So, this would be the loop that you are going to consider, closed loop, meaning your phi goes from 0 to 2 pi. Then because h is along phi, I do not know what is the value of h, but this h is not a function of phi and it is constant for a given value of r, and therefore I can write this as h phi 2 pi r. Now, this must be equal to the total current enclosed, which is equal to I, therefore, this is equal to I, and h is equal to phi hat I by 2 pi r, or B is equal to phi hat mu 0 I divided by 2 pi r, just as what we obtained in the previous case. So, we will show you more examples of magnetostatic field calculation in the next module. I hope you understand the previous calculations very thoroughly. Thank you very much.